All right, so go ahead and try this one out, and when you're ready, we'll discuss. All right, so again, let's split this up by columns just so it's easier to see everything on these slides. Some interesting information. We haven't seen this reaction before. Okay, we haven't talked about this specific type of reaction. But again, relying on our fundamental principles of organic chemistry, we can answer basically anything that's going to be thrown at us. Right? So first question, plausibly, what's an olefin? I've never heard of that. We didn't talk about that in lecture. You might not have come across that in your studying. Not a big deal. You're probably not going to see a question that's just this basic with no context given, right? But it's certainly something to think about. Okay, why is ozone reactive with these ethylene linkages? What reactions might be required for this reaction or conditions? Okay, how might we determine these positions experimentally? Okay, why are nonpolar solvents required for recombination? So a lot of passage information here describing something new that we haven't seen before. We want to be thinking critically about why some of these conditions are the way they are, why certain steps are done the way they are, why certain reactions are occurring, and obviously the diagrams that are drawn are very helpful to sort of visualize what's happening in each of these steps. So look at the right-hand side here. Again, pulling out my questions and my highlighting. Okay, some questions. Why is a reducing agent needed for this reaction? Which oxygen atom is ending up covalently linked to the reducing agent? So we saw this is RAO, this reducing agent oxide. So which of these oxygen atoms is in that RAO? What solvent could be used for this reaction? How would a catalyst affect this reaction? An increase in temperature, pressure, how might any of these things affect the reaction? Right? So with that, let's jump into some of these questions. Okay, interesting kind of question. Something that will definitely require you to sort of think very, very critically about the nature of a reducing agent and what would make something a good or a bad reducing agent. Right? We've talked about how a reducing agent donates electrons, right? A reducing agent reduces its counterpart. Okay, so what we're looking for is something that has electrons to donate. Something that's going to be willing to donate electrons. So either it's electron rich or it's negatively charged, right? So if we look at each of these answer options, we can eliminate a couple of them pretty easily off the bat, right? The proton is definitely not going to be a reducing agent. It doesn't have any electrons. And the silver ion, Ag+, is in the +1 oxidation state. It's actually electron poor right now. It's missing an electron, and so it's actually very unlikely to give up more electrons. And the lead oxide has already really been oxidized. Okay, the oxygens are not going to give up electrons. They are electronegative. They want to hold on to electrons. And the lead has already been oxidized, right? It's already given up electrons to the oxygen atoms. It doesn't really have any more electrons that it can donate. The only plausible reducing agent here would be zinc, because it's in its elemental form. It hasn't given up any electrons yet. It's not electron poor. Now, it's not negatively charged, but certainly of the other answer options, it's the only logical choice. Okay? All right. Let's try this one. Okay, so for this, we're being asked about the reaction in the final paragraph. We'll probably want to go back to the final paragraph to look at what this actually was. And again, as you've seen on a couple of the other sessions like this is actually correct on your notes, but let me just fix it here on these slides. So what are we considering here? In the last paragraph, the student is performing the same reaction as in the rest of the passage, just using a slightly different reactant up front. Okay, the starting reagent is 2,3-dimethylhex-2-ene. Okay? So you can draw that out. That's what it looks like. The relevant concepts here, basically given to us in the passage. The ozonolysis mechanism functionally results in the splitting of the ethylenic linkage and gives us two carbonyl compounds. So you can see that same logic being applied to the 2,3-dimethylhextuene. We're splitting it down the ethylenic linkage and making each one of those a carbonyl. So I should have these two products left over, right? That makes my answer D. So again, you haven't seen, in all likelihood, you have not seen the specific reaction before, but it doesn't matter. As long as you apply, and you can see it wasn't a very high hurdle. It's not like it required you to do lots of very in-depth electron pushing diagram, very, very difficult chemical analysis on this. It's really just basically, at a very high level, looking what structurally does this reaction do to compounds, and just applying that logic to some new compound, some slightly different twist on the original experiment. Okay? So this is as much a puzzle question as it is an organic chemistry question. Don't let these kinds of questions scare you off. You don't actually have to follow all the details of the mechanism. We saw the overall reaction was this, and so that same logic is going to apply. Okay? Remember, the MCAT is never going to require you to know in-depth organic chemistry mechanisms. That's not the point of the exam. The point of the exam is to make you think critically about the information you're given. All right, let's try question number 3. Okay, this is a more straightforward question, less critical thinking here, but it does require you to remember exactly how to find the absolute configuration. So it might require you to get into your head a little bit, again, to think about sort of these three-dimensional structures, but it's not a conceptually difficult question in the sense that it doesn't require you to sort of memorize any specific important information. So what are the stereo configurations of the two chiral centers? Well, let's look at each of them individually. For number 1, so for this carbon atom, if we prioritize these groups, we can see that we're going to have number 1 in the top left corner over there, right here. Why is this one number 1 and why is this one number 2? They're both oxygen atoms because the number 1 oxygen atom is attached to another oxygen atom, whereas the number 2 oxygen atom is attached to a carbon. And so since oxygen is a higher priority, then this top one wins priority. So we've got 1, 2, and then the methyl group is 3. Hydrogen is always going to be 4. These 3 groups are basically pointing out at us, and so the 1, 2, 3 is going clockwise. Therefore, this is R. Okay, so the first answer option is going to be 1R. I've narrowed it down to either A or C. Let's do the same experiment or the same exercise with carbon number 2. This was the highest priority oxygen. Number 2, number 3. Again, these 3 groups are pointing basically out at us. They're going counterclockwise, so that makes this S, which makes our answer C. Let me just fix up this error a little bit to make it match what it says on your slides. And ignore this piece right here. Okay, so our answer here is C. 1R, 2S. Okay, note that these numberings, this 1 and 2, doesn't actually directly correspond to the naming. So this isn't actually carbon 1, or wouldn't necessarily be carbon 1 and carbon 2. We don't actually have to care about the naming here, but it's just how the numbering has been given to us. Okay? Question number 4. Okay, so interesting question. Would this reaction proceed? We're being asked to think about this experiment experimental design. Would this reaction proceed if the student were to use methanol as a solvent to dissolve the 2,3-dimethylhexene-2-ene? Okay, well, the answer is either going to be yes or no, right? And then we need to figure out why is going to be yes or no. So what are we told in the passage? Well, we're told that the carbonyl and the proxy intermediates recombine to form the ozonide in the presence of a nonpolar solvent. Okay, so this is the important passage information. And the critical thinking aspect here is, does methanol constitute a nonpolar solvent? No, not really. It's actually a pretty polar solvent. So we wouldn't expect it to see the formation of the ozonide. Now, it doesn't mean that zero ozonide is going to form. It's certainly likely that maybe one or a couple of molecules, right? But the vast majority of the reaction will not occur. So for all intents and purposes, this reaction is not going to happen in methanol. Okay? So no, we wouldn't see the formation. But next question is why? And the why is that, as we've just said, it has to be done in a nonpolar solvent, right? Now, that option is not given to us, but the only other explanation is no, methanol would act as a strong nucleophile and add to the olefin before the ozone. And that, unfortunately, is beyond the scope of the passage, right? So we don't know that the methanol is going to react instead. So the only other way to still get no is through C. Okay, so a little bit of a bunch of things going on here, right? Identifying key pieces of information from the passage, thinking critically about that information, and then combined with the question itself, and then doing a little process of elimination here between C and D. All right, let's try this one. All right, so what do we expect to see if each of these oxygen atoms of the intermediate between the malonazide and the ozonide are replaced with a nitrogen atom, which peaks would no longer be seen in the IR spectrum? Okay, so if we think about, well, what does that mean? If we look at those molecules, you pull out the oxygen, just replace it with a nitrogen atom. The intermediate has a carbonyl. If you replace it with a nitrogen atom, then you should lose the IR peaks of a carbonyl, right? And the IR peaks of the carbonyl we should see at 1700 to 1800, somewhere in that range, which corresponds to A. Okay, we know the carbonyl peaks are 17 to 1800. Now remember that for all practical purposes on the exam, the only peaks that they ever really test are the carbonyl and the hydroxyl group. It's technically fair game to ask you about others, but the vast majority of questions are going to be about one of those two peaks, as we've seen here. So, takeaways from this passage. The majority of these questions are for passage about novel reactions, right? It's a novel reaction we haven't seen before. So, what are the products, the reactants, the effects of changing the solvent conditions, why experimental choices were made, right? How are the compounds extracted, analyzed, stored? So be thinking critically about these issues as you're reading through the passage, because it's functionally guaranteed that you're going to see questions along these lines for any new experiment or new reaction series. All the questions were answerable with content we've talked about before, right? Spectroscopy bands, finding absolute configuration, basic things, and analysis about reaction conditions, extractions, right? Organic redox reactions. So you had 100% of the tools to answer these questions correctly. Things to remember going forward: don't get scared off by fancy words, these novel mechanisms. They're designed to throw you off. Do not let them throw you off, all right?
For most students, and maybe you too, the CARS is the hardest section on the MCAT. It may feel like it's one of the few remaining obstacles between you and the medical school of your dreams. But as you try to prepare for the CARS, you find there is a never-ending stream of conflicting tips, strategies, and plans, none of which seem to actually help or show any results. If you feel frustrated, overwhelmed, or lost when it comes to the CARS, if you're looking for a CARS expert who has helped thousands of students achieve their MCAT CARS goals, then you found your solution. Testing Solutions MCAT CARS Bootcamp. Founded by Nick Zahner, a current medical student at Stanford with a master's degree in philosophy of religion from Harvard, Testing Solutions' approach to the CARS is revolutionary. Testing Solutions CARS Bootcamp provides day-by-day, step-by-step instruction that teaches you the techniques that produce ultra-high MCAT CARS scores. Instead of wasting your time with the needlessly complex filler that other companies try to sell you, Testing Solutions' approach to the CARS is based on the principle of minimum effective dosage. There's no wasted time, just the minimum amount of effort that is required to get you the results you want. With over 500 4.5-star reviews on Amazon, Testing Solutions CARS Bootcamp is the most trusted, proven, and effective CARS course available on the market today. You will have access to Testing Solutions' 180 meticulously designed CARS passages, the largest CARS practice library offered by any MCAT prep company in the country. Our passages are regularly rated by users on Amazon, Reddit, and SDN as the most accurate non-AAMC CARS practice passages available, consistently rated higher than Exam Crackers, the Princeton Review, Kaplan, and Next Step. Unlike some companies who prey on pre-medical student fears by charging outrageous amounts of money for their mediocre at best practice materials and courses, Testing Solutions will always charge a fair price for an amazing product. Because after all, we're not like the other test prep companies. We're aspiring doctors just like you, only a little further down the path. Let us help you do what we've already done. If you're not happy with your CARS Bootcamp for any reason, we offer a 100% money-back guarantee, no questions asked. You've got nothing to lose and the CARS score of your dreams to gain. Don't be one of the people who write us each week saying they wish they had found our MCAT CARS Bootcamp sooner. You don't have to struggle with the CARS any longer. Sign up and get started today.